Good evening, all of you. Today, I, Naveen Garg from BSc Chemistry in final year, I am going to read a chapter for visually impaired student from the book of NCERT, class 12th, chapter number 15, that is Polymer. Do you think that the daily life would be have a easier than a colorful without the discovery of a varied applications of polymer? The use of a polymer in the manufacturing of a plastic buckets, cups, and squeezers, children toys, packaging bags, synthetic cloth materials, automobiles, tires, gears, and seals, electrical insulating materials, and machine parts has completely revolutionized the daily life as well as the industrial scenario. Indeed, the polymer are the backbone of our major industries, which is plastics, elastomers, fibers, plants, and varnishes. The word polymer is coined from a two Greek word poly means many and mers means a unit or a part. The term polymer is defined as a very larger molecule having a high molecular mass. There, however, refers to as a macromolecule, which are formed by a joining of repeating structural units of on a larger scale. The repeating structural units are derived from some simple and reactive molecules known as monomers and linked to each other by a covalent bond. The process of formation of a polymer from irrespective monomer is called polymerization. Section 15.1 Classifications of polymer. There are several ways of classification of polymer based on some specific considerations. One of the most common classification of polymer is based on the source from which polymer is derived. Under this type of classifications, there are three subcategories. First is natural polymer. These polymers are found in plants and animals. Example: protein, cellulose, starch, some resins, and rubber. Second classification is semi-synthetic polymers. Cellulose derived as cellulose acetate rayon and cellulose nitrate, etc. are usually examples of these subcategories. Classification third, synthetic polymer. A variety of a synthetic polymer as a plastic polythene, synthetic fiber nylon 66, and synthetic rubber buna S are the example of man-made polymer extensively used in a daily life as well as of industry. Polymers can also be classified on the basis of their structure and molecular forces of the modes of polymerizations. Section 15.2 Types of polymeric reactions. There are two broad types of polymeric reactions. First, that is the addition or chain growth polymerization, and condensation or a step growth polymerization. Section 15.21 that is addition polymerization or a chain growth polymerization. There are two broad types of polymerization reactions, that is, in the first type, the polymerization, the molecules of a same monomer or a different monomers add together on a larger scale to form a polymer. The monomers used are unsaturated compound, example alkene, alkylidine, and their derivatives. These mode of polymerization leads to increase in the chain length, and a chain growth can take place through a formation of either of a free radical or a ionic species. However, the free radical governed addition or a chain growth polymerization is the most common mode. Section 15.2.1.1 that is first, free radical mechanism. A variety of a alkene or a diene and their derivatives are polymerized in the presence of a free radical generation initiators. Catalysts like benzoyl peroxide, acetyl peroxide, tert-butyl peroxide, etc. For example, the polymerization of ethylene and polyethylene consists of a heating or a exposing of a light or a mixture of a ethane with a small amount of benzoyl peroxide as an initiator. The process starts with the addition of a phenyl free radical formed by a peroxide to the ethane double bond, thus as generating a new and a larger free radical. This step is called a chain initiation step. As the radicals reacts with the enomer molecule of ethane, another bigger size radical is formed. The replication of this sequence with a new bigger radical carries the reactions forward, and the step is termed as chain propagation step. Ultimately, at some stage, the product radicals thus formed reacts with another radical to form a polymerized product. This step is called a chain termination step. The sequence of the step involves the formation of polythene are despite as follows. First is chain initiation step. Benzoyl peroxide changes to phenyl free radical. Chain propagation step. A phenyl free radical or a free radical reacts with ethene molecule to form a bigger molecule of bigger free radical. Chain termination step. For the chain termination of a long chain, these free radicals can combine in a different way to form a polythene. One mode of termination of chain is shown under as when the two bigger size of free radicals combine to form a polymerized product. The addition polymer formed by a polymerization of a single monomeric species known as a homopolymer. For example, a polythene discussed above is a homopolymer. When the polymer made up of an addition of a two or more than two different type of monomer, a term just copolymer. Example, buna S, which is formed by a polymerization of buta-1,3-diene and styrene, is an example of copolymer formed by the addition of polymerization. The reaction is 1,3-butadiene plus styrene. It gives butadiene styrene copolymer, that is buna S. Section 15.2.1.2. Some important addition polymers. First is A. Polythene. Polythenes are a linear or a slightly branched long chain molecules. These are of capability of repeatedly soften of heating and hardening on cooling and thus thermoplastic polymers. There are two types of polythenes are given below. First is low density polythene. It is obtained by a polymerization of ethene under high pressure of 1000 to 2000 atmosphere at the temperature 350 Kelvin to 570 Kelvin in the pressure of a trace of dioxygen or a peroxide initiator catalyst. The low density polythene LDP is obtained through the free radical addition of a H positive abstraction. It has a highly branched structure. These polymers have a straight chain with some branches as below. Low density polythene is a chemically inert and tough by the flexible and a poor conductor of electricity, hence it is used. In insulator, electricity carrying wires and manufacturing of squeeze bottles, toys and flexible pipes. Second is high density polythene. It is formed when the addition of polymerization of ethene takes place in a hydrocarbon solvent in presence of a catalyst such as triethyl aluminum and titanium tetrachloride, that is Ziegler-Natta catalyst, at a temperature of 333 Kelvin to the 343 Kelvin under the pressure of 6 to 7 atmosphere. High density polythene HDP thus produced consists of a linear molecules as shown below and thus have a high density due to the close packing. Such polymers are of a closed linear polymer. High density polythenes are also chemically inert and more tough and hard. It is used for manufacturing of buckets, dustbins, bottles, pipes, etc. Second polymer is Teflon, that is polytetrafluoroethene. Teflon is manufactured by heating of tetrafluoroethane with the free radical or a persulfate catalyst at a high pressure. It is a chemically inert and resistant to attack by corrosive reagents. It is used in making oil scales, gazettes, and also used for non-sticky surfaces coated utensils. Third polymer is polyacrylonitrile. The addition polymer of a acrylonitrile in presence of a peroxide catalyst leads to formation of polyacrylonitrile. Acrylonitrile in presence of peroxide catalyst polymerization reactions takes place and we get a polyacrylonitrile. Polyacrylonitrile is used as a substitute for wool in making commercial fibers or orlon and arcaline. Section 15.2.2, that is second type of polymerization is condensation polymerization or a step growth polymerization. This type of polymerization generally involves a representative of a condensation reaction between a two bifunctional or a trifunctional monomeric units. These polycondensation reactions may result in the loss of some simple molecules as water, alcohol, hydrogen, chloride, etc., and leads to formation of high molecular mass condensation polymers. In these reactions, the product of each step is again a bifunctional step species, and a sequence of condensation goes on. Since each step produces a distinct functionalized species and it is independent to each other, this process is also called a step growth polymerization. The formation of a pterylene or a dicone by the intersection of ethylene glycol and terpethalic acid is an example, a type of polymerization. Ethylene glycol, that is ethane 1,2-diol, reacts with the terpethalic acid. It gives pterylene or a dicone. Section 15.2.2.1. Some important condensation polymer. First is polyamides. These polymers processing amide linkage are important example of synthetic fibers and terms as nylons. The general method of preparation of consistence of condensation polymerization of diamines with the dicarboxylic acid or a condensation of amino acid or their lactams. Nylons. First is nylon 6,6. It is prepared by condensation polymerization of hexamethylene diamine with the adipic acid under high pressure and a high temperature. We get nylon 6,6 and a trace of O2. Nylon 6,6 is a fiber forming solid. It possesses high tensile strength. These characteristics can be attributed to the stronger intermolecular forces like hydrogen bonding. These strong forces also leads to a close packing and of chain and thus impart crystalline nature. Nylon 6,6 is used in making sheets, bristles or brushes and in textile industries. Second is nylon 6. It is obtained by heating caprolactam with the water at a high temperature. The caprolactam heated to a temperature of 533 Kelvin to the 543 Kelvin, it gives nylon 6. Nylon 6 is used for manufacturing of tires, cobs, fabrics and ropes. Second is polyesters. These are the polycondensation products of dicarboxylic acid and diols. Darcone or a pterylene is the best known example for polyesters. It is manufactured by heating a mixture of ethylene glycol and terpethalic acid at a 420 to 460 Kelvin in the presence of zinc acetate antimony trioxide catalyst as per a reaction given earlier. Dicone fiber is creased resistant as it is used in blending with the cotton and wool fiber and also as a glass reinforcing material in safety helmets. Third is phenol formaldehyde polymer, that is bakelite and related polymer. Phenol formaldehyde polymers are the oldest synthetic polymers. These are obtained by condensation reaction of phenol with formaldehyde in presence of either of an acid or a base catalyst. The reaction starts with the initial formation of ortho and para-hydroxymethylphenol derivative, thus further reacts with the phenol to form a compound having a ring joining each other with the through CH2 group. The initial product could be of a linear product, that is Novalac, used in paints. Novalac on heating with the formaldehyde undergoing cross-linking to form a insoluble solid mass called bakelite. It is a thermostatic polymer, can't be refused or remold. Thus, bakelite is formed by cross-linking or linear chain of a polymer Novalac. The bakelite is used for making combs, phonograph, records, electric switches, handles, or various utensils. Fourth is melamine formaldehyde polymer. Melamine formaldehyde polymer is formed by condensation of polymerization of melamine and formaldehyde. It gives resin intermediate and undergo polymerization gives melamine polymer. It is used for making of unbreakable crockery. Section 15.2.3. Copolymerization. Copolymerization is a polymerization reaction in which a mixture of more than one monomeric species allowed to polymerize and form a copolymer. The copolymer can be made not only by a chain growth polymerization but also by the step growth polymerization. It contains multi-unit of each monomer used in a same polymeric chains. For example, a mixture of buta-1,3-diene and styrene can form a copolymer, that is buna-S. Copolymer have a property quite different from a homopolymer. For example, buta-1,3-diene styrene copolymer is quite tough and it is a good substitute of natural rubber. It is used for manufacturing of auto tires, floor sheets, tiles, footwears, components, cable insulator, etc. Section 15.2.4. First is natural rubber. Rubber is a natural copolymer and possesses elastic property. It is also termed as elastomeric polymer. In elastomeric polymer, the polymeric chains are held together by a weak intermolecular force. These weak binding force permits the polymers to be stretched. A few cross links are introduced in between the chain with the help of a polymer to retract to its original position after the force is released. The rubber has a variety of use. It is manufacturing from rubber latex, which is a colloidal dispersion of rubber in water. This latex is obtained from a rubber tree which is found in India, Sri Lanka, Indonesia, Malaysia and South America. Natural rubber may be considered as a linear polymer of isoprene, 2-methyl-1,3-butadiene, and it is also called as cis-1,4 polyisoprene. The cis polyisoprene molecule consists of various chains held together by a weak van der Waals force of attraction and has a coil structure. Thus, it can be stretched like a spring and exhibits elastic property. Vulcanization of a rubber. Vulcanization of a rubber. The natural rubber becomes soft at a high temperature greater than 335 Kelvin and brittle at low temperature less than 283 Kelvin, and thus shows high water absorption capacity. It is soluble in non-polar solvents and non-resistant to attack by oxidizing agents. To improve upon physical properties, the process of vulcanization is carried out. This process consists of heating a mixture of a raw rubber with a sulfur and an appropriate additive at a high temperature range between 373 Kelvin to 415 Kelvin. On a vulcanization, sulfur forms cross link at a reactive site of double bond and the rubber gets stuffed. In the manufacturing of tire rubbers, 5% of sulfur is used as a cross-linked agent. The probability structures of vulcanization of rubbers are displayed below. Second is synthetic rubber. Synthetic rubber is a vulcanizable rubber-like polymer which is capable of getting stretched twice its length. However, it returns to its original shape and size as soon as external force is released. Thus, synthetic rubbers are either of homopolymer 1,3-butadiene derivative or a copolymer of 1,3-butadiene or its derivative with another unsaturated monomers. Preparation of synthetic rubber. First is from neoprene. Neoprene or a polychloroprene is formed by free radical polymerization of a chloroprene. Chloroprene undergo polymerization gives neoprene. It has a superior resistance to a vegetable and mineral oils. It is used for manufacturing of conveyor belts, gadgets and houses. Second is Buna-N. You have already studied about the Buna-S in section number 15.1.3. Buna-N is obtained from a copolymerization of 1,3-butadiene and acrylonitrile in presence of peroxide catalyst. It is resistant to any action of petrol, lubricant oil and organic solvent. It is used in making oil seals, tanks and linking etc. 15.3 Molecular mass of polymer. Polymer's properties are closely related to the their molecular mass, size, and structure. The growth of a polymeric chain due to their synthesis is independent upon the availability of a monomer in a reaction mixture. Thus, a polymer sample consists of a chain and of varying length, and hence its polymer's mass is always expressed as an average. The molecular mass of a polymer can be determined by chemical and physical methods. Section 15.4 Biodegradable polymers. A large number of polymers are quite resistant to the environmental degradation process, are thus responsible for accumulation of a polymeric solid waste materials. These solid waste causes of acute environmental problems such as remaining undegraded for a quite of long time. In a view of general awareness and concern for a problems created by a polymeric solid waste, certain new biodegradable synthetic polymers have been designed and developed. These polymers consist of a functional group similar to the functional group present in a biopolymers. Aliphatic polymers are one of the important class of a biodegradable polymer. Some important examples are given below. First is polybeta hydroxybutyrate or a beta hydroxyvalerate PHBV. It is obtained by a copolymerization of a 3-hydroxybutanoic acid and 3-hydroxypentanoic acid. PHBV is used in specially packaging orthopedic derivatives and in controlled release of drugs. PHBV undergoes bacterial degradation in some environmental in the environment. Second is nylon 2-nylon 6. It is an alternative polyamide copolymer of glycine and aminocaproic acid and is biodegradable. Can you write the structure of these polymers? Section 15.5 Polymer of commercial importance. Polymers and commercial importance. Besides the polymers already discussed, some other commercial important polymers are along with the structures and their uses are given in a below table. Polypropene monomeric unit. Name of polymer polypropene. Its monomer is propene. Use है manufacture of ropes, toys, pipes, fibers, etc. Second polymer is polystyrene. Monomeric unit styrene. Use as an insulator, wrapping material, manufacturing of toys, radios, and television cabinets. Polyvinyl chloride PVC. Monomeric unit is vinyl chloride. Use is manufacturing of raincoats, handbags, water pipes, etc. Fourth polymer is urea formaldehyde resin. Monomeric units urea and formaldehyde. Its use for making unbreakable cups and laminating sheets. Next polymer is glyptal. Monomeric unit ethylene glycol and phthalic acid. Use manufacturing of paints and lacquers. Next polymer is bakelite. Monomeric unit phenol and formaldehyde. Use for making combs, insulators, switches, handles of utensils and computer dishes.